Okay, good morning. So we are discussing the memory management scheme in the unit number 4. So let us start with the next topic in the memory management. So in that, first we have discussed about what exactly is the memory or how we can define the memory as, right? And what do you mean by the compile time binding, the load time address binding, and the execution time address binding? So already we have discussed one example. For example, the student, we are binding, or the college or the department is binding the student name with the student roll number. So if a particular student is having roll number 5, 6, 7, so that particular roll number is now fixed for total year to that particular student or for that particular semester or for the year. So afterwards, the student is referred with the help of that roll number. Means suppose a department or the staff member want to uh, refer that student or call that particular student, then they are using the roll number. Say for example, absent student roll numbers are there, the present student roll numbers are there, right? So putting the name is a difficult task, but just putting the roll number is a very simple one. That makes various tasks easier as far as the staff member point of view as well as the student point of view also. So it is nothing but one key. You might have studied in database. So it is just a primary key given to that particular data value. That is nothing but the student. So that is so point of discussion is that we are binding that particular roll number to the student. The same way, or on the same ground, we can say that, for example, if that particular process or instruction need to be executed, that instruction must get the exact memory location or memory address, because until and unless that instruction or that particular process not loaded inside the main memory, it will not be executed. So address binding is important. Address binding means actual physical address bind to that particular instruction is very much important, and that address binding took place at three different stages. That is nothing but your compile time address binding, load time address binding, and execution time address binding. That already we have discussed it. So when the program is in a compilation mode, when you compile the program, at the time only the program comes to know what exactly its actual address or the physical address, means where it is, where it will be loaded and from which location, which memory location it will start its execution. Okay, the first point. The load time address binding means what? At compilation time address binding is not happened. The program is loaded inside the main memory, and when it is getting loaded inside the memory, at the time of loading, the program or the process or instruction comes to know its actual address or its physical address. Yes, this is the memory location, and from that particular memory location, the program is going to run there. Now, if the binding is not done at compile time, it is not done at load time, it is delayed till the execution time. Means when program is loaded, program is compiled first, then it is loaded inside the main memory. Till that time, the instruction or the process does not get its actual address, physical address. But when it starts actual execution, at the time of execution, the program or the instruction come to know, yes, this is the memory location where that process is loaded, and from that particular memory location, the process is being executed. So these are the three different, one can say, the type of binding: compile time binding, load time binding, as well as the execution time address binding. Means three different steps are there, right? Now, the next point we have discussed is nothing but the logical versus physical address space. So, physical address space means actual address, it is nothing but your actual address space, or this memory address, one can call it as the physical address. So, this is the memory block. So, this memory block consists of, say, for example, so many addresses starting from 0, 1, 2, 3, 4, 5 up to 1000, or one can say any number depending upon the capacity of that particular main memory. So these are the memory blocks are available. Initial block is available to operating system process. So remember this point: this operating system code is protected. Operating system code, in the sense, operating system processes are protected that with these user processes. Operating system processes, or they must be kept separate here in that particular location, so that the user process must not interfere or must not disturb the operating system processes. Because if they are not mentioned, so for the security reason, for the safety reason, OS processes must be kept separated or isolated as compared to your general user process, and this much amount of memory it is kept for the user process. Any user process can be loaded inside the main memory once it is executed completely. For example, this is the area where the process is being loaded. Once the process loaded, it is executed completely, and as soon as the process executes completely, it will be removed from the main memory, and this particular memory block become free again. And if it become free, the next process will get that particular memory block. This is actually the logic. But the thing is, that here the amount of memory is very less. Amount of memory is very less. Say for example, 0 to 1 GB memory. Though 1 GB memory is available, but this 1 GB is also not sufficient. Or even if it is a 4 GB memory available, but 4 GB is also not sufficient nowadays, because there are some software, there are some application software, there are some system software, or there are some apps. They require huge amount of memory, main memory, to run their applications, right? So if you take any example, for example, you are playing game, so game require maximum amount of main memory. It consumes your maximum main memory. Or some any drawing application, 3D drawing, your drawing, or any CAD application is there, for example, right? Or any drawing application is there. So these are the some applications. They require huge amount of main memory. They require, say for example, 1000 MB, or for example 500 MB memory for their execution, if they want to be executed successfully, right? So the point is that the less amount of memory available, but there are multiple number of n number of processes are there. Processes are much more, and resources is again very less. Or the resources, there is scarcity of the resource, or the limitation of the resources, whereas the processes are in in numbers. So to avoid this thing, what we are doing here, we are having many memory management scheme, or memory management unit is there, that handles all these memory management activities. So for this memory management activity, they use base register and the limit register. Base register is nothing but the base value of the physical location or the actual location, if, which location that program is being loaded. For example, this is, say for example, 100, and if this process is loaded from 100 memory location up to 120 location, 100 to 120 location, so 20 value is nothing but your limit register. 20 is the value for your limit register, and 100 is the value for your base register. Clear this point. 100 is the value for base, means from which base address that process starts its execution, and up to how long, up to how much memory it has consumed. Whether it consumes 120, 130, 140. So we suppose it consumes 140 amount of memory, 100 to 140. So this 40 is nothing but it's the value. It is nothing but the value of limit register, or the limit. So it is the highest limit, or the uppermost limit. 40 MB memory is required for the execution of that particular process. That is the thing. Logical addresses means these addresses which are generated by your processor, logical addresses, and this address space is called as the logical address space, and the physical addresses means nothing but actual address or actual memory address. One can say this is the actual RAM address, is called as the physical address. Logical addresses, we have discussed that. Suppose there is an 8-bit processor, so 8-bit processor means 2 raised to 8 maximum address it can generate, or 16-bit processor means it can generate maximum 2 raised to 16. 32-bit processor 2 raised to 32, and 2 raised to 64. Nowadays, all you are having your 64-bit processors available, so they can have 64 number. 2 raised to 64 addresses they can generate, means it is such a huge amount of logical addresses they can generate, and that is a huge amount of logical address space there. So very simple example, suppose I have 8085 processor, 8085 having the address range is 2 raised to 8, means how much addresses, that is nothing but these 2 raised to 8 addresses it can generate, or 16 means 65536 addresses can generate, or it can generate 0 to 256, 0 to 256 or 0 to 255, one is total 256 addresses it can generate. So I can suppose I want to execute a move a comma b instruction, move a comma b. If this instruction is to be executed and it is loaded, suppose the CPU generates. So what is the first step? CPU generates, say for example, 102 is the logical address generated by the CPU to execute that particular instruction, move a comma b. Say for example, so the zero, how much you have address pool available, or how much address space is available? You have 256 addresses are available, right? Means 0, 1, 2, 3, 4, 5, 101, 102, 104 up to 255 addresses are available, and these addresses are generated by the CPU processor, whether it is 8085, it is 086, whether it is your 386, 486, Pentium 1 processor, Pentium 2 processor, and nowadays you have your Core i3 processor or Core i7 processor, any processor you take, depending upon their capacity, depending upon their speed, they generate the address. Nowadays we have 2 to 64-bit processor, right? So move A comma B address is being generated, for example 102. So logical address means CPU generates 102 logical address for that particular process, but it is not actually the physical address. Huh? Logical means already we have discussed that it is logical means it is a virtual address that is generated by the CPU to execute that particular instruction or to execute that particular process, right? Now that instruction must be loaded inside the main memory. See carefully, that instruction move comma b must be loaded inside the main memory, and when you are copying or when you are loading that instruction into the main memory for the execution, it has some physical address, because in main memory they have its own physical address or its own actual address. So the meaning is that this logical addresses which has been generated by your CPU must be converted into actual address or physical address, right? So the we can say that when address binding is done at the compile time and the load time, this 102 same logical address and physical address is also 102, because these bindings are the earlier binding. We call it as early binding. So they know their actual address before being executed or before being loaded inside the memory. Compile time and load time address binding. But if execution time address binding is there, address binding is done at the execution time, then they don't know actually till they starts their execution, till the process starts its execution. So at that time the logical address must be different than your physical address, right? And this entire scheme, this entire phenomenon is handled by your memory management unit, which consists of your base register and limit register, right? So from this diagram it will be clear to you. Say for example 102 is the logical address generated by that particular CPU to execute that instruction or the process, and its physical address must be different. Say for example the value of the relocation register is, say for example 102 here, and the physical value of and the the logical address is 102 and value is again 14,000. So we can have 14000 and the next limit is 14102. This is the memory location where that instruction is being loaded and from which location that instruction is being executed, right? And this is the value of base register and this is the value of relocated limit register. With the help of this, the instruction or the process is being loaded inside the main memory, and once it is loaded inside the main memory, the process is executed from the memory. So this MMU, memory management unit, is there. Remember this point. So this converts the bottom line which you have to understand or which you have to remember all the time. The memory management unit maps your logical address to the physical address. Remember this point. The conclusion of the discussion, or the one can say that the bottom line of the particular discussion is that logical address generated by the CPU or the processor for any process or for any instruction, it is converted into actual physical address with the help of this memory management unit, that is consist of your base register and the limit register. Clear this point? So mapping to the logical address with the physical address means conversion of logical address into physical address. It is totally done by that particular memory management unit. Okay. So this is the way how the instruction is being generated or the address is being generated for the instruction, and it is loaded inside the main memory for its complete execution. Clear this point? Now we will go to the next point, that is nothing but your dynamic loading. So dynamic loading, in the sense, it is nothing but to obtain the better space utilization, the dynamic loading is used. So meaning is that with the dynamic loading, the is not loaded or the routine is not loaded until it is called. Unused routines never loaded. So all routines are kept on a disk, in a relocatable disk. In the sense, it is nothing but your secondary storage or the hard disk. Main program is loaded inside the main memory and it is executed. So when routine is need to call another routine, the calling routine first check to see whether other routine has been available in the memory or not. If it is not available, then the linkage loader called to load a desired routine into memory and update program address address table to reflect the changes. Then control pass to new loaded routine. So dynamic loading, as the name itself indicates, that it is nothing but the dynamic. Dynamic in the sense, do not load the process or do not load the routine until and unless it is required. Do not load the process or do not load that particular instruction until and unless it is required. Right. So, for example, for a simple example, we can have this much. Say, for example, main memory. Again, consider this is the structure. Main memory is available. Okay, and one routine. Suppose main program. The main program is loaded here. Suppose one program P1 main program is loaded here, and its subroutine is kept on the secondary storage. It requires, say, for example, P2 is the subroutine of that particular program, and it is kept on your secondary storage device. It is kept on the hard disk, right? So you execute this particular process, you execute this P1 process or the main program, and you are giving reference of this P2 program inside the P1 program. And as and when the P2 is required, then and then only you load it inside the main memory. If it is not required, if it is not required for the execution of the process P1, then do not load this inside the main memory. So what you are achieving here, you are achieving the better space utilization, because what happened, unnecessarily, if it is not required, then why unnecessarily you are putting the program inside the main memory, right? So if it is not required, if it is required, no doubt you call it, you load it, and you execute it. But if it is not required, you need not have to call it, and you need not have to place inside here, and why to waste the memory, right? So that's why the dynamic loading says that, for example, you loaded the P1 program, the main program you have loaded, and you execute the P1 program, and the P1 executed successfully, and P1 does not call any subroutine, P1 does not require any file or any, one can say, it does not require any subroutine here. And P1 executed, and once the P1 executed, it will be removed from the main memory, and that particular memory spaces are will be make free or empty used by other process. So why you are loading this P2 process, why you are loading this P2, or why you are loading this, why you are loading this subroutine if it is not required, right? But if it is required, so at the time of execution, in the meantime of the execution of the P1 process or that main program, if it gives the reference to the P2 process, or if it calls the P2, and until and unless the P2 executes and P2 returns some value to the P1 process, the execution of P1 cannot proceed further. At that time, you have to call that particular subroutine P2 and load inside the main memory. Then P2 get executed here, and whatever may be the output value of the P2, that will be copied to the P1, and then P1 will continue its execution. Getting my point or not? Means if it is required by this particular main program or the main routine, then and then only we are going to copy that particular subroutine inside the main memory. If it is not required, do not copy it. Yeah, the very simple word, right? So by using this or by doing this, what we are doing here, we are achieving the better space utilization. We are, because our intention is that this space is very limited. Our intention is that this space is very much limited, and there are n number of processes. So we have to very careful, we have to very precise while using the memory. We, in the sense, operating system must be very much precise. Operating system is very much careful while handling such type of scenario, and one solution is nothing but the dynamic loading. Dynamic means as and when required, then only just call it here. If it is not required, do not call that particular module. It is very simple logic. Advantages: unused routine never loaded inside the main memory. It is useful when large amount of code required frequently, and does not require support from operating system. It is the responsibility of the programmer or the user to design their programs as to take the advantage of such scheme. Suppose you have written a very big C program, or if you have written a very big Java program. So here you have written various sub. Suppose this is the main function, and under this main function you are calling different function. Suppose this is function 1, this is function 2, function 3, function 4, and you make the separate file, and you copy all this function here. So while executing this main program, if they are called, if the functions are called, then and then only you are going to load that function inside the main memory and start their execution. If the main program or if this main function does not need any help from this sub function or the subroutine, do not call this. The very simple, right? So dynamic loading is, as the name itself indicates, that you are going to load the module or the instruction or the process as and when required by the other process execution. The next point is nothing but your dynamic linking. Now, in this case of dynamic linking, so loading is, so here most operating systems support only static linking, in which system language libraries are treated like any other subject module and are combined by the loader. So in this case, it is similar to dynamic loading, but only the thing is that rather than loading being postponed until execution time, linking is postponed. Means in the earlier case, what you are doing, you are postponing the loading, means you are not loading that particular subroutine or the sub function inside the main memory. But here, what you are doing here, you are linking, you are not linking to that particular process, or you are not linking to that particular subroutine here. Dynamic linking means what? The link that particular module, link that particular header file when it is as and when it is required. So very simple example, you have written a C program, right? In C program, you are giving hash, right? Hash include, then stdio.h, stdio.h or math.h file, math.h file, right? So very simple example. So suppose I have written a program of addition of two numbers. Very simple. We take example. Now what I include here, hash include stdio.h file, hash include math.h file. Simple. And then below to this I have written main function, and then add two number, enter number one, enter number two, addition of two number is such and such, and display the result. This is my C program of 4 to 5 lines. Okay. Now I have to execute this particular program. Means, and if I execute the program, so I am going to load that particular program inside the main memory. The program is being loaded inside the main memory here, a.exe. But while executing that particular program, it encounters the function like printf, or it encounters the function like addition operator is there, or scanf function is there, right? So we have to find the definition of printf, we have to find the definition of scanf, and plus operator. Plus means what? How this particular process come to know? Because where is the definition is written? Definition is written in the stdio.h file or math.h file, right? And along with this main program, if I am going to load, if I see carefully, if I am going to load the header file .h file, then what happen? All these header files. So here are only two header files. But if there are such number graphics.h, for example, iostream.h, if there are such a multiple number of header files are there, and if all these header files are to be loaded inside the main memory, the memory become full. Getting my point or not? This memory become full if we are loading this file, header file, inside the memory. Why? Because they are required for the execution of the C program. You cannot find the printf definition. The program will fail to find the definition of scanf, then plus operator or cout. So where to find the cout or where to find the cin function? It is written in iostream.h file. So what I have to do? So shall I load this iostream.h into the main memory? Shall I load the math.h into main memory, or shall I load stdio.h in the main memory? So if I am going to load all the header file, the memory becomes full here with this header file only, and there will be no space available to execute the simple C program. Getting my point or not? So instead of loading, instead of dynamically loading, you have to link it dynamically. Meaning is that when the program come, you execute the program, you need not have to load the header file inside this particular main memory. The solution is nothing but your dynamic linking. So dynamic linking is nothing but, you might have heard about .dll file. .dll file. In Windows, you will find here DLL file. So DLL file is nothing but the dynamic link library files. .dll file are nothing but the dynamic link library files. So meaning is that they are not loaded inside the main memory, but only they are linked dynamically. They link dynamically, and for that timing the link get established, and that particular function get executed, and the link will be removed or terminated. For example, while executing this addition program, when the program counter come to the printf function, and it will search for the definition, what is the exact meaning of the printf, then it will be linked to stdio, that this particular program get linked to the stdio.h file. Definition is fine, and it says that yes, printf means you have to print that line on the screen, right? So if it encounters this plus operator or any minus operator, so it will search inside the link get established with the header file math.h, because you have just included their key hash include stdio.h or math.h. It will search in the stdio.h, it will not find the plus operator. In math.h, it will find that plus operator, and it will serve what exactly is the definition, and the function is perform accordingly. But there is no need to exclusively load the all header files inside the main memory. So instead of loading that particular file, you have to just link it dynamically. And even it is not a static linking, it is a dynamic linking, means as and when it is required, the link get established between that header file or that DLL file. So in Windows operating system, the popularly it is called as the dynamic DLL file. If you go to your Windows folder, you go to Windows folder and you just open it, you will find that .dll file. So .dll files are nothing but the dynamic link library files, meaning is that they are loaded or they are not loaded, they are just linked as and when their function is required or their operation is required in the main memory. They are just linked there, they are not copied or they are not loaded inside the main memory. Getting this point? So that is the main difference. But in case of loading, what you are doing here, dynamic loading, you are actually loading that particular main program, subroutine or the sub function inside the main memory. But linking, you are not going to load, you are just have to link, and that link is to be established at the runtime only in the dynamic in nature. Getting this point? The next point in the discussion is nothing but the swapping. The swapping, why the swapping is important? The concept is very simple. Concept is very simple because swapping is means what? As you know that the main memory cannot accommodate your all the processes, right? So the processes which are currently in a running state, the processes which are currently in execution state, that are being loaded inside the main memory, but the processes that are not loaded inside the main memory, they are kept on the secondary storage, that is called as the backing storage or the hard disk, right? And there is a process, or there is a process, copy the process from main memory to secondary storage and from secondary storage to the main memory. Suppose the process finish its execution, it is not required to be put in the main memory, it will be swap out, means remove the process from the main memory and put it inside the secondary storage, it is called as the swap out. And putting the process back inside the main memory for its execution, that is called as the swap in. The two terms you must remember. Swapping means what? Swap out means out the process from the main memory, and swap in means you are putting process in the main memory, and where you are taking or where you are copying on the secondary storage or on the hard disk. Getting this point? So the process need to be in the main memory to be executed. That is the first basic line. However, it can be swapped temporarily out of memory to a backing storage or to a secondary storage, then again brought back into main memory for continued execution. So when the process is swapped out, its executable image is copied on the secondary storage. See carefully. When process is swapped in, means again when it is kept back inside the main memory, its executable image copied into new block allocated by the memory manager. So swap out process will be swapped back on the same memory space that is occupied previously, and it is depending upon the method of binding. Again, this is the same case. Suppose you are using the process P1, so its initial memory location is, say for example 100, and you are swap out that particular process, and after some time you swap in, means you are putting that process in the main memory after some time. So whether it get the 100 memory location or the memory location change, it is totally depending upon the type of binding. So how the address binding is done with that particular process or that instruction. So if the address binding is done at load time, the process move to the same location of the previous that one. Means if this P1 address binding is done at the load time or the compile time, it will get its previous memory location. But if the address binding is done at the execution time, the process can be swapped to different memory location. So initially it has 100 memory location. Now it may have 203 memory location. It may be depending upon the availability of the space inside the main memory, right? So backing storage is nothing but your fast disk or large enough to accommodate all the copies of the all images of all the users. It best suits to time sharing system. Context switch time is fairly high because what you are doing here, you are spending your swapping time. So see carefully, you are increasing your swapping time means you are reducing your execution time. Very simple word, we can say that you are increasing the swapping time, means processes is swap in and swap out, swap in and swap out from the main memory. That is the time when you are not executing the process. Getting my point or not? So execution means you are not that particular process time is not effectively utilized on its execution, but rather than it is used on the swapping of that particular process. right? Means when you are putting the process swap out and putting it on the secondary storage, you are taking the process swap in and you are putting inside the main memory, right? So you are unnecessarily moving, so that is nothing but the context switching. You are switching process swap in, swap out, swap in, swap out. The meaning is that the process is not currently executed, but it is just swapped, or it is just moved from one location to another location, and you are doing that operation, or that operating system is doing that operation only, and it is not in execution state. Getting the point or not? So this is the way. So this must be avoided, and that maximum time of the process must be spent on the execution. And as soon as the process is executed successfully, it must be removed. It must be removed from the main memory, so that the memory space becomes available to the next process or the new process. That is the conclusion. So the three important concepts, that is nothing but the dynamic loading, dynamic linking, and the swapping is the important one. Remember this point, because this we require in the next discussion also. Okay. So the outcome from the first topic or the first session is nothing but your address binding. We have seen that is nothing but the three types of address binding: compile time, load time, and the execution time address binding. We have seen here. Then there is a logical versus physical address space. Logical addresses are the addresses generated by your CPU, whatever may be the addresses generated, and physical address is nothing but your actual addresses, or one can say these are the RAM memory address of that particular instruction. And there is a mapping. Important point is to be remembered is that we have to conversion of logical addresses. Versus means it is not versus, but you have to convert the logical address into the desired physical address. 101 is if it is the logical address, so you must know, or you must convert that 101 into, say, for any location. So say for example 2543, its actual address, right? So though the CPU generates 101 logical address, but its actual address or its physical address is nothing but somewhat different, right? And this mapping, it is done with the help of your, these are the basic memory management scheme. MMU is the basic scheme with the help of basic register, that is nothing but your relocation or the base register and limit register. Okay. The next point is nothing but your dynamic loading. So load the module as and when required. If it is not required, do not load that module or do not load that particular subroutine. If it is not required, you keep it on the secondary storage, and when it is required, then and then only you have to load that particular module. And linking means what? You are not going to load, or you are not going to link that module, or you are not going to link that particular file. As and when that file is required, link that file. For example, yesterday.h file is there, or math.h file. So these are the header file, or these are the supporting file which are actually required for the execution, but they are given just a reference. They are given just a reference. As and when their reference come, you just go to that particular file, you take the reference and continue execution of your main program. Do not load or do not link earlier, right? So that is nothing but, and why we are using this thing? So why we are using this dynamic linking, dynamic loading? So for better space utilization, the main intention or the main objective is that we have to achieve the better space utilization, because the resource is very limited, and that resources must be shared between the multiple number of processes. And how to achieve this? So these are the various schemes, or these are the various ways how we can have the better space utilization or better resource utilization. Proper word we can say that this is nothing but the better resource utilization, we can say that, right? And the lastly we have seen the swapping. Swapping means you are using secondary storage as a backing store, all right? So because all processes cannot be accommodated inside the main memory, so as and when the process get the CPU for the execution, then and then only you just swap in the process from the secondary storage, and when its execution completed, or when the process enters into the waiting state, remove the process and swap out on the secondary storage. So swap in and swap out is the basic one can say the concept. But in that case, what we have to see that we have to also ensure that the maximum process time must not be wasted on the swapping of the process in and out from the main memory. All right. So if you are spending, or if you are wasting your time on the swapping itself, then execution of the process remains as it is. So ensure that the process must spend maximum of its time on the execution rather than the swapping in and swapping out. So under the CO, that is CO4, course outcome is to understand the various memory management technique that we are already going on. The questions explain the concept of address binding. You have to write the three methods. Give the significance of logical and physical addresses. So draw the diagram of memory management unit CPU diagram. Already I have shown to you. That diagram you have to mention, and you have to explain logical as well as the physical addresses clearly. Write a note on dynamic loading and dynamic linking. So these are the references. Definitely you have to only go for the Galvin, that is nothing but the reference book. Do not go for any local author book. So thank you. So we'll stop here for the today.